Hello everyone, welcome to another video. In this one we're going to be looking at 6.2 linear relations. So the first thing we have is a definition of a linear relation. So it says a relation is an association between two sets of elements. So there's two kind of terms in there you might not know. A set, all a set is it's a group of items. Okay, so that is a group. And then elements are just different items in the group. So sets are a group, and then your elements, they're just items. Items can be numbers, they could be shapes, they could be heights, they could be ages, it can be anything. The next thing it says there is it can be represented in 6 different ways. So we're going to look at 6 different ways down below here for how to represent a relation. So the first one is through words. So you're literally going to say it in words or write it out in a sentence. So we have 3 times the length of your ear, which we're representing as E, is equal to the length of your face, which we're using the letter F. So with that one, you literally just describe the relation with your words. The next way to do it, and this is using the exact same example, it's talking about the length of your ear in relation to your face. This one we use an equation. So we have F equals 3E, and that's 3 times E. Then we have ordered pairs. So these are pairs that are ordered in a particular way. So the first number here is called the independent variable, and the second one there is called the dependent variable. We're going to look at those definitions later, so you don't have to know that for now, but that's just the order that it goes. And it follows kind of the same thing that we had for the equation there. To get to that second term, just like within this one, we were going 3 and we were timesing by E. To get to this one, we are also timesing by 3. Same with this next one. To get from 4.5 to 13.5, it's just been multiplied by 3, and each of these, it's just the exact same thing. So that's an ordered pair. Then we have our table of values. So for these, you're going to have, again, your independent variable on the left, and then your dependent variable on the right. And to get from one side to the other, it's just multiplying by 3. These are the exact same numbers, as you can see, as what we had up top here. They're the exact same down here. So that's for our table of values. We could also represent a relation using an arrow diagram, and this one is very similar to a table of values. It's just not in a table form. So instead you just have arrows, and again the independent variable is on the left, the dependent variable is on the right, and to get from one side to the other, it's just multiplying by 3. And then lastly we have a graph. So I'm sure you've seen of some graphs before. These, you're going to have your independent variable on the bottom, and then your dependent variable is going to go on the vertical axis there. So this is the horizontal axis, that's independent variable. This will be dependent variable, and that's on the vertical axis. So you can see in the example, if you had, say, an ear length that was 4 centimeters, if you times that by 3, you're going to get 2, and you can't see it on here, but this is going up by 4s. So that's going to go 8 next to 12. So if you had ear length of 4 centimeters, if you times that by 3, like we were doing up above, your face length is going to be 12 centimeters. So now that we know the different ways of how to represent our relations, we're going to look at some different types. So there are 2 types. You could either have a linear relation or you could have a non-linear relation. So it says there linear relations form a straight line. So that should be fairly easy to remember. Just think linear line. Okay, and this happens when you plot the data on a graph. So if you took all your data points, plot it, it's going to form a straight line like this one right here. A non-linear relation does not form a straight line when the data is plotted on a graph. So that's going to be something that has some type of curve. Okay, as long as it has any type of curve, it's going to be non-linear. If it's absolutely straight, it's called linear. So it's easy to visualize if we were to graph it like this, straight line for linear, non-straight line for nonlinear. In terms of a table, for the linear side, it's going to have consistency or it's going to have a pattern. So when we went from 2 to 3, it was adding 1, 3 to 4, adding 1, 4 to 5, adding 1. When I look at the y values, it went from 8 to 11, that added 3, 11 to 14, added 3, 14 to 17, it added 3. So there's consistency, the pattern doesn't change. So with each one of these, it always increases by the same amount. Whereas when we look at the nonlinear side, so here it's going up by 1, but if I look at the y values, it's going to increase by 19, and then it increased by 37, and then 61. So there's no consistency. The pattern doesn't stay the same. It's changing from one to the other. And then the last type that we're going to look at is different equations that are written here. So all of these ones here are linear. These are all examples of nonlinear. And we're going to look at them to kind of note the difference between them so we can use this to check new ones that we get. So all of the ones on the left side, if you were to look at the exponents, they're all going to have an exponent or a degree of 1. So all of them have a degree of 1. Whereas you look at the degree or kind of the power on the right-hand side ones, that one's got a 2, that one's got a 3, and then this last one, both of those have 1s. So if we were going to find the degree of that, you'd go 1 plus 1. So that tells you that the degree is equal to 2. So if that's degree 2, it can't be linear. So all of them have to be degree 1, like all of these ones here on the left side. And then just one added example I'm going to do here, because this one's a little tricky. If you had y equals 1 over x, now looking at that one, you might be thinking, well, this has a 1 and this has a 1, so that's going to be degree 1. But this is not in the numerator. If I were to change that and put it in the numerator, if I were to flip that up using our exponent rules, when it moves up, it's going to change to the negative. So this is actually y equals x to the power of negative 1, and that is not degree 1 like all of these ones on the left were. So those are examples for linear and non-linear relations. Then we're going to look at some different types of data. So you can either have discrete data or you can have continuous data. Discrete data, as it says there, is data values on a graph that are not connected. So if we were to look at this graph here, I can see it just goes from one point to the next. None of these points are connected. Whereas continuous data is data values on a graph that are connected. So it's one solid line, there's no gaps, it's constant the whole way. That is called continuous data. It is continuous data that is connected, no gaps. Okay, so for discrete data, the way to remember this is I think of the letter D goes with dots. So you're always going to have dots on your graph. And then with continuous data, think of a continuous line. Moving from there, we have our independent and dependent variables. So I talked about these before. Now we got the actual definitions of them. So an independent variable, it is a variable for which values are selected. So you get to pick these variables. So an example of this would be how much you study. So if you wanted to study a lot for a test, you could study a lot. Hopefully that would help you do better on the test. If you wanted to study very little, you could do that too. That would be your choice. You are selecting how much time you want to study. Whereas the dependent variable, this is a variable whose values depend on the independent variable. So if our independent variable was how much you study, right? If you would study a ton, hopefully that's going to help improve your mark and it's going to affect what you get for your mark. Whereas if you hardly studied any, the mark you get might not be as high. Now, that might not always be the case, right? It just kind of depends. Maybe you're really good at math and you don't have to study much and you still get a good mark. But you could think of it in terms of a sport. Your independent variable could be how much you practice, and then your dependent variable would be, depending on how much you practiced, you might maybe perform a lot better during a game. So looking at some examples, if we had it in a table of values like the one here in green, so the x's, those are our choices for independent variable. Those are always going to go on the left side. And then the corresponding values for the dependent variables, that's written down here, those are going to come out on the right side. Okay, so the way they got each of these values down here, I'm just going to do one. So the first one we had for our formula, it was y equals 3x plus 5. So that's 3 times x. I'm just going to put a blank for the x and then plus 5. And I'm going to write in the x value. And I got to choose that x value because it was an independent variable. So I'm going to put in a -1. So I got 3 times -1. That's just equal to -3. And then I still have that plus 5. And then when I add those two together, I just get +2. And that's how they got this +2. That's also how they would get this 5 and this 8. They just plugged them into this formula, and then it gave out these values. So that's why they're called dependent variables, because these values depended on what value you put into it. And then if we were to look at our dependent and independent variables in terms of a graph, our dependent variable is going to be on the y-axis, that's the y-axis, and then our independent variable, those are the ones on the x-axis. So again, this is the x-axis, and this one going vertically, that is the y-axis. So now that we're done all that, this is going to bring us to our first example. So in the first one here, it says a frog can jump 2 meters per jump and can maintain this distance on each jump. So what that just means for maintaining his distance on each jump is that he's not going to get tired. He's going to continually jumping 2 meters for every jump. So part A, identify the relationship between the number of jumps and the total distance as linear or nonlinear. And we're going to do that down here. So maybe if you want to think about it first, try to guess whether you think this is going to be linear. Remember, linear followed a pattern, it was consistent. Or if it was nonlinear, where nonlinear was where it didn't follow a pattern. So maybe it added 2 and then added 5 and then added 7. It changed every time. Okay, so hopefully you tried to guess that one, but in this case it's going to be linear because the jumps are the same amount each time. So we're just going to write that. So because we had consistent jumps, it's going to be linear. Now in part B, it says create a table of values and choose variables for the relation. So remember, on the left, this is going to be our independent variable. And then on the right is going to be our dependent. And I'm going to go ahead and just change everything in this question. I'm going to change all my colors to be blue. So we needed to choose our variables. Now in this case we have the number of jumps that we're going to be taking, and we're also going to have the total distance that we have traveled. So the number of jumps, this is going to be the independent variable because we get to choose how many jumps we're going to be doing. So number of jumps, that's going to go on the left side. And then the dependent variable, that is the total distance, because depending on how many jumps we take, we are going to travel a certain amount of distance. And then I'm just going to write my units for these. So this is going to be meters. And we also needed to pick a variable for these. So number of jumps, I'm going to use the letter n, just because n goes with number, so number of jumps. And then total distance, I'm going to use the variable d. So our number of jumps is represented as n, and our total distance is represented by d. So let's start to fill in our table. So we could have, at the very beginning, we could have 0 jumps. And if I did 0 jumps, I'm going to have 0 distance traveled. Then I could have 1 jump, 2 jump, 3 jump, and so on. We're going to go up till 5. Our distance traveled, if I did 1 jump, remember it's only going to be 2 meters for every jump. So after the first jump, I'm going to have 2 meters. Then I'm going to have another 2 meters, so another plus 2. So I'm going to be at 4. And then another plus 2, and this is just going to continue. So it's going to go 2, 4, 6, 8, and then 10. It's just adding 2 every single time. So we're done with part B. We're going to move on to part C. So it says create a graph for the relation, and I can use all of these points that I just came up with. So I'm going to go from 0 all the way up to 5 on my independent variable. Remember, independent variable went on the horizontal axis. So that's going to go on this one right here. So I'm going to label 1, 2, 3, 4, and 5. And I'm going to put the variable that I was using, and that was n. So n represents the number of jumps. I could write that down here as well, number of jumps. Then for the vertical axis, that was the dependent variable here. So that is going to be our total distance, and it's represented by d. So I'm going to put d here, and this is the total distance. And it was being measured in meters. And then I'm going to write the measurements that we had, and it went up by 2. So I'm going to go 2, 4, 6, 8, 10, all the way up to 12. Okay, and then I'm going to start to plot my points. So the first one I had there, it was at 0 and 0. So that's at the very, very start there, 0 and 0. Then we had, it was over 1 and up 2. So that is going to be right here, over 1, up 2. Then next we had at 2 and 4. So I'm going to be 2 over, that's right here, and then 4 up. So that gets us to there. And we're just going to continue this. So at 3, we're at 6. 4, we are at 8. And then 5, we were at 10. So there is our graph filled in. And then we just got one last question here. So it asks, should we connect the dots? So what do you think? Do we connect the dots in this case, or do we leave them separate? So if you had a little trouble with that question, I'm going to kind of pose a different question that might make it a little bit easier. So when we were at this point, to get to the next one, that was the next jump, and I was up at the 2 meter mark. Then when I was at 2 jumps, I was at the 4 meter mark. So each of these was just a jump, and it told me what my distance was. Now, could you hypothetically have, say, half a jump in here? You could not, right? You either didn't jump or you jumped. You can't partially jump. So you can't have any of the points that are in between here, and so you can't draw a line connecting it saying that there are points in between there, because you can't have partial jumps. You either jumped or you didn't jump. So let's write that as our answer. So it is no, you can't have half or part of a jump. So just because it looks like they look like they're on a straight line, don't just go ahead and draw a line in there. Think about, could you have points in between? If you could, then draw a line. Now we're moving on into our second last question. So number 2, it says, determine whether each relation is linear, explain why or why not. So if you want to try to guess these ones first, you can go ahead, and then I'm going to go through them. So the first one, I look and I see I got this exponent of 2. As soon as you see an exponent of 2, that means it's degree 2, and it has to be degree 1 for it to be linear. So in this case, we can say it is not linear or non-linear. And then our reasoning for this is because it is degree 2. For part B, we have the set of ordered pairs. So for the first one, we had 10 and 12, then 15 and 4, and then 20 and -4. So if I look at the independent variable, I went from 10 to 15, and then I went from 15 to 20. So in the first time, it added 5, and then the second time, it added 5. So that would be consistent. With the dependent variable, it went from 12 to 4, so that minus 8. And then from 4 to negative 4, that also minus 8. So in this case, it has that consistency. The pattern isn't changing, so it would be linear. So all that pattern means is that it changed by the same amount each time. So number 2 is finished. We got our very last question here, number 3. So in number 3, it says, consider the relationship between the cost to rent a dance hall and the number of people attending the dance. If the hall charges $200 plus $5 for each person who attends. So part A, is this relation linear or non-linear? And if you want to try to go through this one, you can on your own, and then I will go through it. So whether it is linear or non-linear, in this case it is linear because the price that I'm charging is going to start at $200 just for the hall, but then every person after that, it's just going to be $5, $5, $5. So that is being consistent, it's not changing. Then part B says, assign a variable to each quantity, which is the dependent or independent variable. So I'm going to assign the number of people that attend this dance as n. So n is going to be the number of people that attend. So that was right here, the number of people attending the dance. And then the other thing that we needed to give a variable to was the cost to rent the dance hall. So I'm going to use the letter C, capital letter C, and that is going to be the cost to rent the hall. So part C, it says assume 24 people attend. What is the cost? So if 24 people attend, that is our variable n. So I know n is equal to 24. So we are going to be paying $200 up top here, right off the bat, plus $5 for each person that comes. So our cost, we're going to write a little equation for this. It's going to be $200 right off the bat, plus $5 for each person that attends. So I'm going to multiply by the number of people that attend. So I got that right there. And then what I can do is I can substitute in n as 24. So I got 200 plus 5 times 24. So that is going to equal 200 plus, and then 5 times 24 is 120. And then adding those two things together, we're going to get 320. And that was dollars. So our cost is $320. Very last question now. It says, is the data discrete or continuous? So discrete meant, are you going to have dots on your graph? And continuous meant, is it all going to be connected in a line? So what might be an easier question to think about is, think about what n was. N was the number of people who attend. Could you have partial people that attend? Could you have like 1.5 people that attend? Well, of course not. So therefore, you can't have a continuous amount of people that attend. It's either you have one person that attends, 2, 3, 4. There's no kind of middle. There's not like a 1.5. There has to be a whole number of people that attend. So our answer for this is going to be discrete. So that was our last question. At the bottom here, I'm just going to write out our textbook questions.